All right, hi everybody, I'm Rebecca, and these are my friends, Tall Aaron and Not So Tall Sarah. And they are going to help me demonstrate to you the idea that size doesn't matter. That's right. When I say that, I mean that even very small molecules, even very small biological molecules can do things that are important and exciting. So I'm going to explain this to you in the context of enzymes. So what is an enzyme? An enzyme is just something that makes a chemical reaction happen more quickly than it would happen if things were just randomly bumping around, knocking into each other in solution. Okay, that's all an enzyme is. So Aaron and Sarah are enzymes. Aaron, being very tall, is going to represent a large enzyme with a lot of information. He took a lot of time to evolve. He's got a lot of surface area. He's got a lot of moving parts. He's pretty cool. He's more the kind of enzyme that we have in our bodies today in our cells doing things, and we're going to see a little bit of what Aaron is capable of in a moment. Sarah, well, Sarah's a small enzyme. She's very small. In fact, she's not the kind of thing we normally think about when we think of an enzyme. She doesn't have that much information in her. She's very simple. Okay, so I'm going to ask them both to carry out a chemical reaction. So I'm going to ask them both to draw me a picture. All right, so please, both of you, draw me a picture. Wow, that was really fast. Wow. Look what Aaron drew. That was, you know, this is very beautiful. Aaron, let me ask you, can you draw anything else other than this? No. No, he can't, okay? He's really, really good at doing this one thing, and he does it really fast. And that is something that we consider a characteristic of an enzyme when we think of enzymes normally. Okay, Sarah, how you doing over there? Are you? Well, let's see what you've got. Okay. Sarah, no, this is really good. Okay, this is really nice. This is really nice. So Sarah, it took her a long time to do this, and you know, maybe it's not as specifically defined as what Aaron did, but you know what, I still really like this. I'm gonna hang this on my refrigerator. I think this is important and this is relevant. So this actually happens in life. In the lab, actually, we have experiments where we've shown that this happens. Okay, you can have very small, very tiny enzymes. They actually catalyze reactions that are relevant to biology. What that means, it's not that hard to make life necessarily, and maybe that means that it isn't that hard for us to find life elsewhere. Thank you. Thank you, guys.
Thank you, and thank you to the volunteers as well.
Yeah. Thank you, props.
Yeah. Judges.
Well, that was really fun. Very creative, and a lot of good raw material you're working with. I think you could take it a lot farther. I got the sense that you have not practiced it a ton of times, and it works, but it just, I don't know, I felt like it's so good. I mean, the humor and the use of props and the interaction, and the story, the content, there's real science content that people are learning, going, makes you think. But I just felt like you could take it further. Like, I wanted to follow up on, you asked Tall Aaron if he could do anything else, and he said no. And then I got the sense part of the punchline was probably that short Sarah could do lots of different things, even though her things weren't the Mona Lisa.
It's amazing how fast the time goes.
But you didn't quite get to it.
Exactly.
And so, I mean, it's a challenge, but I felt like if you had refined it, you could just get that much farther with it.
Thank you.
Thank you, David, for helping me focus my thoughts there. I think it got really interesting in your last 30 seconds, where you're talking about how it might not be that hard to find that life exists in other planetary environments. So I think if you could tighten up the front end of your 3-minute presentation and perhaps hint at what you're going to be getting at the end, that will help you to improve your presentation. But yes, indeed, very entertaining.
Thank you.
You know, you always want to be careful that you don't lose the message through the media. And here's just something you might want to think about, because I love the tall Aaron, I love the short Sarah. That and the fact that you already had the Mona Lisa, you know, ready to pull out, that was great. But here's the thing. I thought you could make a point about the smiles, because the Mona Lisa smile is this enigmatic sort of thing that people have been thinking about forever. And it's very complex, and it's got a lot of layers. And so Tal Aaron doing that and as his only thing, then contrast that with the simplicity and the power of the smiley face, and that's what you want to put on your refrigerator, because it makes you smile too. And that's so important, to start every day with a smile. So the fact that her simple thing was more important and easier to understand than his complex thing, I think maybe would have kind of clarified what y'all were thinking is, oh, you can tell I'm in Texas again. It's starting to slip out. That might be the clarity that really makes this sing.
Thank you.
Thank you.
Anything that DNA and protein can do, RNA can do better. DNA, RNA, and proteins are the ingredients that our cells use today. And so when we think about the origin of life, or how easy is it for life to arise, we can look at some of the things that are in our cells today, and we can ask ourselves the question, what kinds of ingredients or what kinds of molecules were kicking around in, you know, this alleged primordial soup, and how could life get started? And specifically, how many different flavors of molecules did you need to get life started? So let's look first at DNA. Could life have started just from DNA? Well, DNA is really good at storing information. It's really, really good at storing information. It has a sequence based on its chemical composition. This can be replicated. It's very, very stable. It's kind of like a big, giant dictionary, a big reference book. But the thing about a dictionary is it's not good for that much. I mean, it's really huge and heavy, right? And all it's really good for is looking up and extracting information. DNA can't catalyze reactions. It can't make chemical bonds break and form. It's not very good at that at all. And so that is one of the features that we think is really important for life. DNA can't do it. What about proteins? Proteins are actually really good at catalyzing reactions. That is what they're specialized for. But there's no information really in a protein. A protein cannot make another one of itself. So proteins are not a very good candidate for one of the very, very first biological molecules. But what about RNA? RNA is like this piece of paper with paper by Steve Benner on it. And I'm going to do this, not because I don't like Steve Benner, but RNA is structurally similar to DNA, so it also has information in it. But it can do this. Okay? It can stick to itself and stick to each other and make these really interesting shapes. And these shapes can catalyze reactions. They can react with other molecules. They can break bonds. They can make bonds. And that is why RNA is thought by many to be a very good candidate for one of the very first biological molecules. You don't need DNA. You don't need proteins. All you need is RNA. And because you only really probably need one flavor of molecule to get life started, this is why we think that maybe it isn't that hard for life to get started elsewhere in the universe. Thank you.
Thank you, Rebecca. Lisa, let's start with you.
So if it's not that hard for it to get started, why is it so doggone hard to find it?
Well, I mean, I'm talking about life forming maybe on the basis of single-celled organisms, at least to start with. And it would be hard to talk to a single-celled organism. Yeah, it's hard to find because of, detection levels. I don't know how one would find an RNA that's across the universe.
David?
I like the use of the piece of paper as a prop. Really fun. I won't tell Steve that you did that. This is probably not fair because it might be a really long answer, but if it's possible, in a short answer, so if you started out with just RNA and you didn't need DNA and proteins, how did you get from there to life that needs both?
Well, so RNA, I like to think of the RNA world as really an RNA world that is interacting with little bits and pieces of the other molecules. For example, amino acids, which are the subunits of proteins. So I'm saying that the DNA and proteins certainly didn't exist in the forms that they are now. The RNA could have existed in a form much like the form that we see now. Does that get to your question? Thanks.
Linda.
I have one quick question, because your talk really intrigued me, and I want to talk to you more about it, but we can't do that right now. And the question I want to ask, if what we think we understand so far about the origin of the first self-replicating biological molecule is a 100-piece puzzle, how many pieces of the puzzle do we have on the board so far?
For a self-replicating molecule or organism?
A molecule.
A molecule, we have, RNA can extend another RNA pretty long, almost up to 100 units long. So that part has been done. It's still not perfect, though. We still have to do a lot more work on it.
How much do we understand about how the first one came to be?
How the first one came to be? That's harder to get at because, for example, that one that I just mentioned, that RNA enzyme, it itself is pretty complex, right? So we still need to find out how you can have a short, relatively short RNA, which is making more of other RNAs. So that part we really, we definitely need to do a lot more work on.
Thank you, Clan MacLeod.